but yeah, so we also went over how reinforcement learning is it's kind of like in a different ballpark. It's more of a it works based on like an agent and an environment. We'll go over that later in the year. And so as our example model, we chose linear regression. You know, it's a regression model where you input a continuous value and it outputs you a continuous numerical value. Um, I went over it. Well, everybody at TAMS pronounces it epochs, but I searched it up and it's pronounced epics. So I'm just gonna pronounce it that way because that's the like I guess etymologically correct way to pronounce it.
You're
Um,
epic.
no, Joaquin's more epic than me. But yeah, we went over loss function and loss. And this is also something I just wanted to touch over a bit more. So remember, let me pull up Paint. Uh, I talked about the two loss functions that I talked about are the mean absolute error, MAE, which is just the absolute value of the error. So it looks like this. And then MSE, which is mean squared error, which is just the squared value of the error. You know, it look more like this, right? But the reason I want to go over this in particular is because Kaushik made a good point last time, where if you know say you're using MSE, which is a pretty common loss function template, right, for linear regression, and Kaushik said how you know if you're using MSE to like say predict these, and you have this one outlier here, right? If your model tries to come up with this line, it's going to have a very large error due to this one outlier because you know the distance is very large here, and when it becomes squared, it becomes much larger. And so with that one particular outlier, you know, it may cause a model to be a bit more imprecise and turn out like that, even though you can tell from the data, you know, it should be closer to this, right? To follow most of the trend points more closely, your model may end up, you know, doing something like this to try and um, make up for that one particular outlier value. And so here, let me pull up this article. So this shows other types of loss functions, you know, outside of just mean average error and mean squared. And so, you know, he has the ones I talked about, mean squared, mean absolute. But then it also has something called the Huber error. Where is it? Oh yeah, Huber loss. And basically it's like a good middle ground between means the mean absolute error and mean squared error, right? Where green is actually no, these are all forms of Huber loss. But basically, is it? Oh, there's no like. I think there might be a graph at the end here. Where, yeah, here. Okay, this is kind of confusing. Let me see. Okay, yeah, you can actually make them out. So, you can see from the orange. So this here, this mean absolute error, and then the red is the mean squared error, right? So those are the two we were talking about. And then for the Huber, it's a middle ground that allows you to select basically how rounded the error function looks like. And so those are like the yellow, the like slightly orange and super bright yellow. Two shades of yellows are. These are two Huber loss functions, right? And the reason you might want to use these is because they're still rounded at the bottom, like the mean squared error is. So that would incentivize it to get a good middle ground between several values, right? But at the same time, it's not super huge. Like it's not ginormous at very large values, like mean squared error is, right? Because, like for example, right here, you know, mean squared error might be somewhere all the way up here, right? That'd be a very large loss if you're using MSE. But Huber, you know, the further you get away, it tapers off a bit. It doesn't become as large, and therefore it doesn't punish outliers as much. And so, you know, from that example earlier, where you have that one outlier, if you're using Huber loss, it wouldn't be as bad if you're using that instead of MSE. And so I just wanted to go over that real quick. And then we went over bias and variance, which are different measures of, or different sources of errors um, in machine learning problems that arise from model complexity, right? Where, you know, when you have a model that makes a lot of biases about your data that are incorrect, you know, it may have a lot of error there, or if it makes too few and it has a lot of variance, then it may have more error there. You know, you have to find the good middle ground between those two. We went over underfitting, overfitting, and yeah, just those two. And you know, where underfitting is where your model doesn't learn the inherent values of the data you're trying to find, and overfitting tries to fit the model too closely to the data, and it finds like arbitrary, you know, non-existent patterns that it thinks it finds there, just because you're trying to fit it so hard into the data. And then balance, which is like, you know, where you find the patterns that you want and not any extra non-existent, just arbitrary patterns you might have found. And then we talked about hyperparameters, which are the higher level parameters of the model that control how it learns. You know, these are the parameters that are optimized by people rather than the model. We talked about regularization a bit. We're going to go over that more in this meeting, but it's basically a method to reduce overfitting and reduce variance in your model. And then, yeah, we went over handling data, so data types, feature scaling. This is particularly important because a lot of models use gradient descent or distance-based algorithms to be able to make their predictions. And then what to do in the case of missing values. And so, you know, we talked about, you know, we could do nothing, drop rows, drop columns, or imputation, right? Or you could do imputation plus imputation flag. For this one, we're also going to go more in depth. In particular, we're going to talk about mice. So here in the examples for imputation, you see we have, let me take this out. Mean values, most frequent, nearest neighbor, placeholder, multivariate imputation by chained equations, and machine learning. And so mice is the second to last one, multivariate imputation by chained equations. And I just think, I'm not gonna lie, I just think it's pretty cool, and I thought it'd be interesting for y'all to learn how, because this is definitely not something that I was taught as when I was learning how machine learning models, or learning about the basics of machine learning. So let me see. Okay, so I don't know how big I can make this. So let's say we have a data set that actually, yeah, we'll just ignore this one. So let's say we have a data set that has 3 values, or 3 columns, right? So 3 features. So it'd be like age, gender, and income, right? So for here, it doesn't really matter which ones are features and which ones are labels. You know, we'll just say income is a label, but for mice, it doesn't really matter, right? So you're trying to predict the income from the age and gender. And so this would be a 0. So these would be our data points, right? Our entries. And so the first one, you know, say age is like 23, male, I don't know, 38K, right? Next one would be, I don't know, 19, female, 17K, 42, female, 89K, whatever, right? And say that we happen to have some missing data, right? And one of the assumptions that you have to make with mice, you know, for it to be able to work most effectively, is that I forgot the specific name of this, but you essentially have to assume that the data that's missing is missing at random, because the missing data could become missing from a variety of ways. Like, for example, if you're collecting data from a variety of sources, and one state or one province or whatever just doesn't record the gender, right? They only have the age and the income. So this one would be like 37, and this would be this one's just empty. So NA or NAN, income 73K, right? So just one like province or state doesn't record gender. That would not be missing at random, because you know, there's a correlation there, right? You know where the source of the missing data is, and that's from that one particular data source of that one state or province that you know didn't record that. And so in that case, it might not be as effective. So let's say like another missing value is here, right? Like we don't have the age for this one. Oh, this one's male and I don't know, 10K. And then for the last one, say like income is missing, right? So we have 21, female, NA. Okay. So we have this data set that's missing a bunch of data from a bunch of different sources. So what is it? So MI stands for multivariate imputation by chain equations. So the first thing that we do here is that we create a copy of our data for every feature that has a missing, has any missing values. So in our case, we have all three columns here, all three features are missing values. So we create 3 copies of it. Right? If we only had age and gender missing, we'd only need 2 copies. You know, if we only had 1 missing, then we'd only need 1 extra copy. So say like, you know, we have, this is 1 copy, this is the second, and this is the third, right? And so for each particular copy, we're going to focus on one of these missing features. And so since we have 1 copy for each feature, let's say this one's for age, this copy of the data set is for gender, and this copy is for income. And so let's focus on the age for this first one, right? So the age data set. So this one has, let me copy this. So we have this data set. This is looking crusty. So I have this data set, right? That's a copy of the original that we specified for age. So since we specified it to be for age, the first thing that we do is that we use a simpler method of imputation, right? And so for this example, you know, we're using age. So for a classification, or our classes column, which is gender, it's you know, it has 2 classes, male and female. Let's just use the mode, right? The most frequent class. And so here we have 2 males, 3 females. So the most common class there is female. So I'll just replace that one with female. And then for income, you know, we'll just get the mean for this class, right? These are just simple, like basic imputation, like replacement functions, right? I don't know what the mean of this is. I'll just say like 42K, all right? So then what we do here is we have this data set that has imputed values on every single feature except for the one we're focusing on, which in our case, we're focusing on age, right? So next thing we do is that we split the data set into two separate ones. So first, we split it into the 2 data sets, one of which includes all the included values, and the other one of which includes all the missing values, right? So the first data set would basically look like this. You see, and then take this out. Wait. Okay, whatever. I can't make this look nice, but the first one would look like this, and then the second one would look like this. Since we only had 1 missing value, the second one is you know, it's just one value long, right? 1 data point. All right, so now we have these 2 data sets, and what we do here is we use this included data set as our training, and this missing values data set as our testing, right? And if you remember from last time, you know, training is what your model learns from, testing is where your model actually performs its predictions. And so what we do here is our missing column here is age, right? That's a regression. That would be a regression problem because it's a numerical continuous value. So here, say they use some model to be able to predict the age. based on the other two included features, right? Gender and income, right? And keep in mind that these also have like basic imputed values, right? Imputed values using like very basic, simple equations of like the mode and the mean. And so when we want to train our model to be able to predict the age, we use this, we use this data set as training, right? And once we have a trained model that's able to predict the age, then we go into our missing values data set and try to predict all the missing values for age based on their included values, right? So let's say that for this one, it says, oh, it's male and they make 10K. That's most likely to be a 31-year-old, right? So then now we have, so now what we have is all the data we need, like fully imputed, but only the age is imputed like smartly, right? The other two values are still imputed like sort of in a dumb way, right? Because the method we chose is really simple, just mode and mean, right? So we introduce this this now like smartly imputed value back into the data set, right? All right, and now we have this data set, and that's what I don't know where this came from, but that's what becomes of our age data set, right? So now our age data set has all imputed values with only the age being imputed smartly and the other two values being imputed, I guess, dumbly, or whatever the adjective would be for that, or adverb, right? And so this was the example just for age. We do the exact same thing for gender and income, right? So then gender will result in a data set that has a uh, gender column, gender feature imputed smartly, and the income data set will include an income feature that is imputed smartly, right? And so now we just want to take the best features of each of these data sets and introduce them back into our original, right? So for age, remember we have all the age values imputed smartly. So here, let's say that from our age data set, it said that this particular value it predicted to be 16, right? So this one, oh, it predicted 16. And then from our gender data set, we get all the missing gender values. So here we said, oh, this one it predicted to be female. And same thing for income, right? We take the income values from the income data set. So, oh, it said this one is 25K, right? And so now we have all these, I guess, smartly imputed values, right? And so now the next step is to just repeat that basically over and over again, right? So make like 3 more copies of this data set, do the impute again based on the other values, and then insert them back into the original, right? So except this time, you don't have to use any sort of dumb imputation, right? You already have all fully imputed values. So like if you're to do this for a second cycle, you know that this particular value needs to be replaced. This was imputed, right? But instead, you can use these newly updated smart values for the other two values to make a better prediction and update, a better prediction for what this value should be. So let's say after a second cycle, with these using these newly imputed smart values, the model says, oh, I think this should be 18 instead, right? And then it updates the other two the same. And then you can just keep cycling through this as many times as you want, right? And that's a parameter that you can set. So you can specify in advance, oh, I want you to perform mice for 10 cycles or 16 cycles or whatever. And so we just continue, you continue along this route for as many cycles as you decide to include. And so, that's basically how mice works. I'm sorry, I don't have we probably should have an entire slide for this. But besides that, it's probably going to be pretty difficult to remember all that without writing it down. So we'll have the recording available later. So I think that was it for this particular. Yeah, that was it for this presentation. Now we can start with this week's. And so last week we started with linear regression as sort of an example model. That started so we could apply some of the concepts that we learned. But now we're gonna look more deeply into it. This is gonna be the first lesson where we go like actually into the math behind how it works. And yeah, we'll just do that, and then we'll also finish up some data science and machine learning from last week that we didn't get to cover. And so we're gonna review last week's content. We're gonna talk about. So this is we already did the review from last week. This is some of the content, like the data science stuff that we still haven't gone over. So like train validation, test data split, k-fold cross, and leave one out validations. We're gonna go into linear regression, right, an in-depth look, and then we're gonna walk through a code example, right? And we'll also upload like the code in the data set for y'all to use. And so, yeah, so this is continuing our review of data science from last week. And so, oh yeah, this is Kaushik's slide, never mind, yeah, my bad.
You're good. So essentially like train, validation, and test, these are 3 types of data that when you have a data set, you basically want to split it up in some sort of way that has a bit of data left for each of these guys. Normally, like a decent metric is usually to do like 70% train validation and then 30% test, or maybe 60-40. And there's different techniques for splitting your data so that, well, not necessarily split your data, but you can split it multiple times and train it multiple times over each different type of split. And so to go more specifically into what each type of data is, training data is essentially the data that your model will repeatedly pass through itself in order to learn how to get an error each time and see what weights or whatever it has to update in the neural network. Or like, let's say it was, or Henry, do you know how it would do it in linear? Like it'll take its error, right? And it'll update the, what is that? The
linear regression in particular, like the one we're gonna learn, it only goes through one epoch. Like it doesn't go through it over and over again.
Okay. Well, I guess linear regression, it doesn't go over multiple times, but at least from the example of neural network that I know, it'll essentially take this train data, and that's the data that you are going to, your model's going to learn from. And if you see the chart on the right, the training error always goes down, because as your model keeps learning more and more, I guess the model's complexity almost goes up because it keeps going through the data. It'll eventually, it'll just keep going down, but at some point you're going to begin overfitting. If you remember from last time, overfitting is essentially when you overtrain it on one specific data set. So it creates correlations that shouldn't really exist. And that's when validation data comes in. Validation data is also part of that, like, how I said earlier, 70%, 30%. Validation data is part of that 70% as well. And that validation data, it essentially, because it's a new data set almost to the model. So because it hasn't learned, it hasn't actually used it to learn, the validation is like a good control almost for you to be able to measure how good the model is doing at that specific point, using some sort of loss function. And as you keep going forward with more and more learning, or I guess epics, is it like k-means validation? What do you mean? Oh, we have like different types of validations. Like, are you talking about the? Can you elaborate on your question?
Are you talking about like k-means clustering? No, this is different from that. Yeah, like Kaushik was saying, validation is just another split in your data set.
But there's, if I don't know when we would go over that. Henry, is that like part of what we should be going over this time?
A k-means?
Yeah.
We'll go over that probably later when we go over like unsupervised learning.
Okay. Well, the validation data is just a little branch off of your train data. Yeah, and it's, as you can see in the graph on the right, like the error for validation, if you can move the paint window, yeah, it essentially just like goes back up. And that's because your model is only training on the train data. So at some point, when it's overfit, when it begins overfitting, the validation error just hops back up because the predictions are no longer accurate. They're too closely fit to your training data, so that they're not good enough to work on other data sets. And then test data is the last of all of these, and that's what you would use at the end of your entire training to figure out how accurate your model is. It's more or less what you would use to evaluate your model. And essentially by splitting these in different ways, you can find like a balance between how much training, validation, and testing you need. Testing is just, the only reason you'd want to have more so that you can confirm your tests. And if you put too much data into your train and validations, you're not going to have enough test data to actually prove that it's a working good model. Next slide.
So yeah, this is kind of what it looks like generally. So like, where this is your entire data set, right? You'd split like 70% of it to your training and validation, and then 30% to your testing. And then within training and validation, you can do whatever, like another, I don't know, like 70% split. Right, and like Kaushik said, you train on your training data. Then after a certain amount of, or after every epoch, you validate it. And this is data that hasn't trained on, it hasn't seen before. So this is what you use to determine if it's overfitting or not, like this graph shows. Because yeah, since it's training on your training data, it's always gonna underfit, or it's always gonna lower the loss. And the reason you have validation and testing data separate, because this is a question I first had when I was learning about validation data. Why do you even have like validation data in the first place if you have testing data for that? Well, that's because the reason you have testing data separate is because even though the model never directly sees the validation data, it still affects the learning of the model. Because what you use is a metric to determine when it's overfit or not. So it still influences the model itself. But the testing data, on the other hand, the model literally never sees ever until it's completely done training and validating and stuff.
Wait, and I think you like lagged out for a second.
Oh, really? Oh, what'd you miss?
I don't know. I don't know what the last words you said were, but it's fine.
Yeah, I was saying that like the testing data is data that the model has literally never seen, like at all. It doesn't ever see it until it's completely done training and validating. And yeah, since the validation data has influenced the training of the model, it's better to use a separate testing data to evaluate it at the very end.
Do you want me to go over this, or you got it?
You can go over this.
Cool. So k-fold cross-validation and leave-or-not validation, these are different ways of like splitting up your data set, and I think this is what Ajay was talking about, maybe. Because yeah, and so
yeah. The K-means says something else.
No, he did. Oh yeah, okay. Well, he DM'd me, but essentially like the k-fold cross-validation is just a way of, once you have your what's it called, training data like split, you need to when you have you figure out how much you want to split your train and test to, you realize how you take, like, let's say you have 70-30, right? You can actually like take multiple splits of 70% and 30%. So Henry, this might be easier to do through paint actually. Even the image on the side, right? The bottom right, if you see the beginning portion, the test data is those first 5 bubbles, but the training data is those remaining bubbles. Then the second iteration, you run this all through the model once again, but you choose the second 5 bubbles, and then the remaining data becomes your training. And so you just go through all of those different splits. And when you do that, you essentially have the model train over almost like 5, it's not really 5 unique data sets, but it's like to the model, it's almost the same as being unique data sets. And so it'll basically be able to use, it'll account for more variability then, because you have more data that you're training off of essentially. Even though it's the same amount of data, you're just training over it in different ways. And there's 2 different levels for splits, right? For what Henry showed in the earlier Microsoft Paint thing, there's the split that you have between training and test. And then within your training, you also have the split between training and validation data. That's kind of confusing, but essentially you have 70 and 30%, right? If you put the 30% off to the side, you can split the 70% training data into another split of 70 and 30%. And so that means in both of those layers, you can do k-fold cross-validation. And that's just like one way of kind of like increasing the amount of data that you have almost to pass through the model, or the number of iterations that you have in terms of training it. And so the reason it's like this k value in k-fold cross-validation is exactly like how many sets you split your train into. So in this case, if you have, if k is 5, right? Or I guess in this image on the right, the iteration is k. So if you are choosing 5 bubbles, right, and you go down 5 every single time, and there's how many, 5, 10, 15, 20, then that'd be like a k of 1 second.
4.
Yeah, k 4. Henry, can you take this real quick? I have to go for 1 second.
Okay. But yeah, so like imagine that you have, you know, you split your data into 2 sections. One is for testing only, and then the other is for k-fold cross-validation. This is your validation slash training set. So like Kaushik said, you split it into k separate sets, right? And you split it, you basically divide it equally. So if you want to divide it into 2 sets, so your k is equal to 2, then you have, you know, you have this one. Actually, let me, right? You split into 2 sets, right? And these 2 sets for your training and validation. You basically switch between them for every iteration of k-fold cross-validation you do. So yeah, like the thing here explains, you know, first you train a brand new model on the left set, right? Oh, this is not the right tool. The left set as training data, and then you use the right set of your, you know, training slash validation. Use the right side as validation data for your first iteration, right? And so this would be like creating a brand new model, and you know, doing the training on here and validating on here. And then since your k is equal to 2, you go over it a second time, right? You go through it again. But this time you switch it over. So now your left one is validation and your right one is training, right? And these are 2 separate models, right? This one's a new one that you create for this iteration, and this is one that you create for this iteration, right? Then from there, you can test them both on the testing data, and then you can, you know, evaluate the performance, like average them or do whatever you want with all that data. Right? Usually you just average the performance of all your trained models, right? And so, you know, for more examples, right? If you wanted to do a k higher than 2, say you wanted to do like 5-fold cross-validation, 1, 2, 3, 4, 5. So then for your first iteration, you know, you'd use this as your validation data, this as your training, everything else is your training, you know, and just go down the line with that, right? So next one would be like this second one is your validation. Oh, wrong tool again. Right, and then for your third model, it'd be this one, et cetera, right? And so there's also, so what happens if your k is equal to your number of entries in your data set, right? So like say that you have 100 data points here, right? 100 rows in your training data, right? Then you have like 100 splits, right? That'd be a bunch of splits, right? So that basically be saying, you know, use everything except for one particular data point as training, and then validate on that last particular data point, right? And then do it again except with the second. Do it again with the third, do it again with the fourth, do it again with until you reach n, right? And then particular is called leave one out cross-validation, or leave one out validation, because you're just leaving one value out of your training data to use for validation, right? And this concept of splitting it into k sets and going from one to the next for each iteration, it doesn't have to apply only to training and testing, right? You can have like nested cross validations. So say here, right, you want to do 2 layers of cross validations. So the way that would work is you have your entire data set, right? And so your first layer of cross validation would be to determine which one is your testing data. So then say you choose like 5. So 2 for 5, right? And so for your first iteration, you do this one as your testing, right? And then the rest of this, right, for your second layer, that'd be choosing among the rest of the data. Oh, whoops. So this rest of the data. So from here, right, then you go through another layer of k-fold cross-validation, where like for your second one, say you do like 7. Actually, no, that'd be too hard to draw. Let's do like 3, right? So this left one in this iteration would be this one, would be the left one, and your validation for this iteration would be this one, right? And then the rest is training, right? And then you could, and then you do this entire thing for your second layer of validation. Oh, my thing's not big enough. Here we go. Right, so then you switch between them for your second layer of validation, and then everything else would be right. And then once you're complete with this entire set of iterations in your second layer of cross validation, then you can go to your next iteration of your first layer of k-fold cross validation and do that whole thing over again. So now you had your original 5 splits of testing and validation / training data. So now this one becomes a testing data, and then the rest of it gets k-folded, right? And then you do the whole process over again where for this remaining data you do another layer of k-fold. And this is just another way to be able to implement that for both testing and training data. Although I will say that this generally this does increase like the training time by a lot, because k-fold cross-validation increases training time by if you're thinking of terms of like space complexity, then it'd be O of k, right? Because instead of training the whole thing once and then validating and testing, now you're training it the whole thing k times and validating and testing that many times again. And so doing this double layered like nested k-fold would be like k squared, O of k squared, right? If you had the same k for both, because for each k, you're doing another whole set of iterations, and then you do that whole thing k times, right? And so for models that take you a while to train, like if you have some complicated architecture for a neural network that takes a while to train, having this nested k-fold cross-validation, or even a single layer of k-fold cross-validation, could take the training time from a couple days to like a couple months. And so yeah, that's one of the cons of k-fold cross-validation. And so this is the last part of the data science review, which is the confusion matrix. And so this whole thing, okay, I know this looks pretty scary. It's pretty complicated. By the way, if y'all have any questions about what I said before or anything, just say it in chat or unmute your mic or whatever. But basically what a confusion matrix is it's a way to measure the performance of a classification model. And so, a matrix that maps a number of predicted positives and negatives against the actual positives and negatives. So let's look at this graph here. right? And so on the left axis, we have the predicted class, right? So say you're trying to predict, you have an image and you're trying to predict whether it's an image of a dog or not. So the predicted class would be what your model predicted for it to be, right? This is what your model said. So for this top one, which is true, this is saying, this is your model saying, oh, this data point was a dog, right? This image is an image of a dog. This bottom one is false, where your model is saying, this is not an image of a dog. All right, so this is the predicted class axis. The top one here is the true class axis, also known as ground truth or actual truth. And, you know, like the name suggests, it's the actual classification of the picture, right? It's whether it's actually a picture of a dog or not, right? So regardless of whether your model says it's a dog, this is regardless of whether your model says it's a dog or not, right? So if you have a picture of a dog, then, you know, that'd be true here in the left side. If you have a picture that's not of a dog, then that'd go on the right side here. And so, you know, that creates these four quadrants, right, which are different mixes between these two. And so the way these are named is that the second word in the name suggests what the model predicted. All right, so if you see here, the predicted class, the top one is for when the model says it's positive, right, when it is a dog. So these ones are called the positives, right? And the same thing here, which is the negatives, right? So these are when the model said this is not a picture of a dog. And then as for the prefix here, the left word, the first one, this prefix tells you whether the model was right or not, whether it was correct. So in this quadrant, you can see that true class says this is a picture of a dog, right? It's an actual picture of a dog. And the model said that, yes, this is a picture of a dog. So this means that your model predicted it correctly, which is why it's called true positive, right? Over here, though, on the right side, this is when it's not a picture of a dog, but your model said this is a picture of a dog, right? So it could be a picture of like a cat, and your model says this is a dog. So that's obviously wrong. And so since your model said positive, you know, it said this is a dog, and it was wrong, it's called false positive, right? This false means that the model was wrong about its positive prediction. And then we could just go down the line with the other two, right? So this is when the model says it's not a dog, when in fact the true class is that it is a dog. So this is false negative. And then this is, you know, when they're in agreement. The model says that it's not a dog, and the actual picture is not a picture of a dog. And be true negative. Okay? And so, you know, that example that I gave you was for binary classification, which is when you only have two classes to predict from. And so there's several different ways to measure to see how good your model is. Like basically there's different metrics that you can make out of these numbers, right? So first one we're gonna go over is accuracy. And so, you know, without thinking of it in terms of you know, true positive, true negative, false positive, false negative, how would you determine the accuracy of a model? You know, regardless of, you know, ignoring this, how would you do that? Well, for a classification model in particular, right? Um, you would take how many it got right over how many it predicted total. And you can see why this is a good metric for accuracy, because how many got right over how many got total is telling you what percent of all the data did it classify correctly. So if out of 10 data points, it classified 6 of them correctly, it's 60% accuracy, right? So, you know, if you feed it data, then you can be 60% sure that it's going to classify it correctly. And that's what we have here. So this equation down here is this CA I don't know why it's CA instead of like AC or ACC or something, but this is accuracy, right? And so what this says is that true positive plus true negative over everything else, right? And this true positive, true negative. When you add them all up, you basically get every single prediction that the model made, right? So these are the correct predictions over all the predictions. And so, yeah, like I explained earlier, this is a metric for if you gave it some data, how likely is it to predict it correctly? And so the next thing, the next metric you can get from this is called precision. And this is a measure of how well you can trust positive classifications from the model. So what does this mean? So what I mean by how well you can trust positives is if the model gives you a positive classification, how sure can you be that the model is right? And so how would you find that? So first of all, you're trying to find, this isn't within the context of positive, classifications, right? So out of all the positive classifications that the model gave, these two would be all the positive predicted classes, right? So true positives plus false positives, right? These are all the times that the model has ever said, yes, this is a dog. Now, out of all those times, how many times was it actually correct? And the answer here is that, it's true positives. That's how many, how many correct positive classifications it got. So that's why that's the equation for precision here. It's true positive over all the positive classifications, all positive predictions. So that would be true positive plus false positive, right? And so as an example here, let's say that you've been tasked with creating a machine learning algorithm that can tell whether someone or not has a bomb in their suitcase or in their luggage, right? So what would be the accuracy and, well, actually, let me build one real quick here. Let me see. So let's say, we have the same graph here, right, where this is predicted and this is actual. So let's say you've been tasked with finding, creating a model that finds out whether or not somebody has a bomb in their luggage. So let's say that these are your data points. 20. Okay. So if you remember, this is true positive, this is true negative, this is false positive, this is false negative. So what would the accuracy be here? Let me see. Oh, not calendar. Here, calculator. Right. So the accuracy here, if you remember, is just how many got right over how many predicted total. So here would be 120 plus 398, 518 over plus 5 plus 398 plus 38. 561. So 518 over 561. It gives us a 92% accuracy. So this tells us if you're to give them a random passenger, inspect the suitcase, how likely is it to get the prediction right? And this tells you, oh, if you give it a random passenger, it's 92% likely to predict whether or not they have a bomb or not correctly. Right. So in most applications, this would, well, actually it depends on your application, but let's say this looks pretty good, right? Because out of 92%, you can just have an additional check by like a TSA agent or something. So now let's see what the precision is, right? And so for our case, since we're predicting if a passenger has a bomb or not, a true positive would mean that the passenger has a bomb and the model said they had a bomb. And a false positive would be if the passenger did not have a bomb, but the model said they did. That'd be like a false flag. So then, if you remember, the equation is true positive over, so how many positive corrections, how many positive classifications it got correct, out of how many positive classifications it made total. So that'd be 96% precision. So when you look at this metric, it seems even better. Like if somebody, if your model said that somebody has a bomb, you can be 96% sure that they do have a bomb, right? Their positive prediction is 96% trustworthy. And so, but there's a flaw in this system and the way that we're measuring this. And that's where the last thing comes into play, which is actually second to last thing, which is recall. And so what recall is it's how well the positive class is actually predicted. So what this means is that if you were to give the model a passenger that does have a bomb, how likely is the model to say they have a bomb? And so, so this would be for all the cases where the passenger does have a bomb. So for the true class, these are all the true cases, right? It would be true positives and false negatives, right? Because true positives is when the model, when they did have a bomb and the model got it right. False negatives is when they did have a bomb and the model got it wrong. And so if you're trying to see out of how many positive classifications the model predicted correctly, you'd use all of their correct positive predictions over all of the positive classifications total. So in our case, let's say here there's a total of plus 38, 158 people who had bombs in our, in our run here, right? This is like test data, right? And so out of all those 158 people that had bombs, how many of those did the model say had bombs? How many did it predict correctly? So that'd be 120 over 158. This is 76%, right? And so for our particular use case, where we're trying to predict whether a passenger has a bomb or not, false negatives would be really bad. And the reason for that is, if a passenger has a bomb and the model says no, and they get past the model, or they get past the TSA agent, and they make it onto the plane, that's really bad. That's catastrophic if you get too many false negatives. And so, yeah, exactly. Then the plane blows up and people die. And so for our case, false negatives would be, that would be like the worst case scenario. Like that's what we want to definitely avoid the most. And so in this case, that's why we'd want to use recall as a metric, because recall, it says, it prioritizes how well the positive class is predicted. So how well people with bombs are caught, how many of them are flagged, right? And on the other side, we have false positives, and the consequence for that is relatively low compared to false negative, because false positives would be somebody doesn't have a bomb, but the system says they does. This would be, a TSA agent searches their bag and they find no traces of bombs, right? And then they just continue into the flight. That's just a waste of like 5 to 10 minutes for the TSA agent and the passenger. So that's a much smaller consequence for our example. And so, this is why you'd want to prioritize these different things, right? So you'd want to prioritize recall if you want the model to be able to predict the positive classes correctly, and use precision if you want to be able to trust the model's positive classifications, right? If you want, if the model says they have the bomb, you want to trust that they have a bomb. right? And so let me give another example that highlights the other side of this, right? Say that somebody comes up with a COVID vaccine, right? And the COVID vaccine, it's effective. You know, people who have COVID, sorry, not a vaccine. Let me say a cure. That's better for bio kids. Um, so yeah, somebody who has COVID takes a cure and they're COVID free, right? But if somebody who doesn't have COVID-19 takes the cure, then they just die, right? So in this case, you want to build a model that predicts whether or not someone has COVID-19. And so let's see. Let's say we had these same numbers for that problem, right? 120 people who did have COVID had it predicted correctly. 5 people who didn't have it had positive prediction. 5 people who did have it went under the radar, and 398 people who didn't have it, you know, they got predicted as not having it. So here, we want to prioritize having low false negatives. False positives. Now, why is that? Well, in our case, the consequences for false positives are a lot higher than false negatives. Because what false positives means is that you give a false flag to someone for having COVID, right? They don't actually have it, but you say they do. Now, if you say someone doesn't have COVID and it leads to them being administered the cure, you know, and they don't actually have it, then they just die, right? But on the other hand, you know, if you don't flag someone as COVID, even though they do have it, then you know, they just have to suffer through COVID. But that's still, even though it does have a risk of death, you know, depending on the person, 1 to like 20% chance of death is a lot better than 100% chance of death. So here, right, in this case, if your model says that somebody has COVID, you want to be really sure that you can trust the model and that they do have COVID. Because if your model says that someone has COVID and it's wrong, then that person would die if they were administered the treatment. And so here in this case, if you remember, the precision was 96%. So if your model says someone has COVID, you can be 96% sure that they actually do. Right? And then the last thing here is F1 score. And so what the F1 score is it's like a combination of these two metrics, so precision and recall. And if you've done like competition math or something, then you might competition math, then you might not know what the harmonic mean is. But if not, it's fine. So the harmonic mean of a set of numbers is this formula, right? For a set of numbers like a of an, right? And so, you know, if you have like 5 numbers, then it'd be 5 over 1 over the first, plus 1 over the second, plus 1 over the third, plus 1 over the fourth, plus 1 over the fifth number. And so the reason we use harmonic mean instead of just the mean of the two is because using this type of mean instead of the arithmetic prioritizes having both of them relatively high. Because for a regular mean, if you had like let's say like your precision was 1 and your recall was like 0.7, right? That would result in a mean of 0.85, right? But for our use cases, we generally want to have both of them relatively high, right? We'd rather have, instead of having a 1 and 0.7, we'd rather have like a 0.81 and a 0.86, right? And that's what this you know, this harmonic mean prioritizes, right? It prioritizes having these like two both relatively high measures for recall and precision, rather than having one high and one low. Similar to kind of similar behavior to mean squared error. And so this is the formula for F1 score. And you know, this, if you just like directly took the 1 over precision plus, or sorry, 2 over 1 over precision plus 1 over recall, right? You could use that, but this is basically the same formula, just with some algebraic manipulations to result in this simpler formula. And then yeah, I spent a lot more time on these slides than I thought I would. So the last thing we're going to go over today is generalizing confusion matrices for non-binary classification. And so, you know, this is what it looks like. And so let's break this down. Let's see. So the axes are flipped on this one. In case you get confused, then you can just tell me or ask a question. But basically here, the way you do confusion matrices on non-binary classification, and so this is classification with more than 2 classes, you do it on a class-by-class basis. And so for our example here, we have our classes C, right? C is our set of classes, which is n long, right? We have n classes in our set C, and the subscript K represents the current class that we're getting the confusion matrix on, right? So let me get another example of, actually not ABC, that'd be a bit too abstract. Let's see, you're classifying dogs. One, you're classifying, you have 3 classes. One is German Shepherd, one is Beagle, and one is Husky, right? So these are 3 classes. So let's use the same, you know, same axis flip as I use here, just not be confusing. So this would be the predicted truth, and this would be the actual truth, right? And so actually, let me write this down like this: German Shepherd, Beagle, Husky. And this would be actual, right? And so let's say for this one, we're focusing specifically on Beagle, right? This would be our CK, right? So if we're focusing on Beagle to make a confusion matrix out of, there's 9 possibilities here. And so let's go over the corners first. So say that it was not Beagle, right? The actual class, sorry, I meant here. So the actual class was something other than Beagle, right? So that means it was somewhere here or somewhere here. So if the actual class was not Beagle, then your model can either predict it to be a Beagle or not a Beagle. So for here, this is German Shepherd. This is essentially saying not a Beagle is the actual class, and the predicted class is not a Beagle. All right, so this would be true negative. And then, you know, you do the same thing on the other corners, right? So German Shepherd is not a Beagle. It predicted Husky, which is not a Beagle. And I know this may seem confusing because intuitively, it seems like these 2 should be different classes. Because here it predicted German Shepherd correctly, but here it thought that the German Shepherd was a Husky. But remember that we're focusing specifically on Beagle. And so we're not focusing on the relationships between the German Shepherds and Huskies. We're only focusing on the relationship between either of them and the Beagle, or the Beagle class. So here, you know, we have the same thing. The actual class is not a Beagle, and the predicted class is not a Beagle. Actual class is not a Beagle. Predicted class is not a Beagle. All right, and then we go through the same motions that we did before with you know, false positive, false negative, true positive. So here in the middle, right, this is the case where the actual class is Beagle and the predicted class is also Beagle. So this would be true positive, right? Right, it got it correct. And now for these 4 corners, or these 4 sides actually. All right, so let's start on the left. So this is when the actual class is Beagle. So when the image is of a Beagle. However, the predicted class on these left and right sides says it predicted something other than Beagle. So if the actual class is positive, but it predicted a negative class, so its class prediction was negative. If you remember, that's the second word in the name for it. And it got the negative prediction wrong because it says this is not a Beagle, even though it is a Beagle, and that's a false negative, right? So this is where it is a Beagle, and it said no, this is not a Beagle. And now we can do the same thing on the top and bottom, right? This is when it's not a Beagle, but it says yes, this is a Beagle. So this would be positive prediction, and the class is wrong, right? It's not a Beagle, even though it said it is, so this would be false. And so this is essentially how you'd come up with a second diagram for coming up with these confusion matrices for specific classes. And like I said before, this is on a class-by-class basis. And so you have to do, for a multi-class confusion matrix, you have to do it in relation with one of the classes. So you can't just get a single confusion matrix for the entire, for every single prediction, right, regardless of a class, because you don't know which class you're doing it with the perspective from. So for example, yeah, you would have three matrices in this case, right? So yeah, you'd have a matrix for the German Shepherd class, a matrix, you'd have a confusion matrix for the Beagle class, and a confusion matrix for the Husky class. And for multi-class classification, you can't have that because say we have the same three classes, right? And you want to have you have the same classes. Actually, let me just reuse that same one. So you have the same three classes, but you want to come up with a confusion matrix for the entire, all the predictions in all the classes, right? Oh God, this is taking a while. There you go. So how would you start? Well, for one, if you have a German Shepherd and it's a German Shepherd, then you know that's predicted it correctly. All right, true positive. Beagle and Beagle, true positive because it predicted it correctly. Husky and Husky, true positive. Okay. So now, what about the other squares? Well, look at this top one. If you have a German Shepherd and it predicted it to be a Beagle, you know it's wrong, right? So it'd be false something. However, since you're not doing it from the perspective of any class in particular, you don't have any way to tell if it's a false positive or false negative, right? Because if you're doing it from the perspective of a Beagle, then that'd be a false positive, right? Because the actual class was not a Beagle, but you said it is a Beagle, so it'd be a false positive. However, if you're doing it from the perspective of a German Shepherd, you're doing it from the German Shepherd class, then that'd be false negative, right? Because the class is, yes, it is a German Shepherd, and the predicted class is not a German Shepherd. So predicted was negative, right? And so since you're not looking at it from a particular perspective, you can't really know if this is a positive or negative. So you can't really give any classification to any of these squares, which is why you can only have a confusion matrix from the perspective of one particular class. However, what you can do here, however, is get the accuracy. Because if you remember, accuracy is only all the true classifications that it got right over all the classifications it got wrong. And since you know all the classifications it got right, and sorry, not all the classifications it got wrong, over all the classifications. Since you know all the ones it got right, and you know all the classifications it made, then you can get the accuracy for the entire, for the entire data set, all of your training data results. But yeah, I think that's all, honestly, for today. Yeah, also one last thing. So this, this graph shows like a generalization of just a simple binary classification. So if you notice, if you cut this so it only has 2 classes, it ends up looking exactly the same as the other graph, right? Well, this one has the axes flipped, but you still get the message, right? So it shows how this is only a particular case of this generalized version of the confusion matrix. And so yeah, from there, you have this on a class by class basis, so you can use it to tell how well your model does for each particular class. If you wanted to be able to, tell beagles in particular really effectively, right? Then you'd make a confusion matrix for beagle, and you'd see how much of the recall is, right? And if it's like 99%, you're saying, oh, out of all the beagle pictures, it said 99% of them were beagles, right? And then and yeah, so this is how you can see all these metrics for different classes in your classification model. So yeah, unfortunately we didn't get to the rest of the lesson. Yeah, we'll just continue that next time. Does anyone have any questions? Because if not, then
if not, like if you have any later as well, you can always just message us.
yeah, you can just like ask in the group chat. Yeah, I know this was a lot, and it might have gotten kind of confusing at parts. So please ask questions if you don't know what's going on. But yeah, if there's none, then you're just free to go now. Actually, you were always free to go. We're not like holding you hostage, but the lesson's over now.
All right, thank you.
Yeah, no problem.
Can you stop the recording, Henry?
What'd you say?
Can you stop the recording?
Oh yeah.
Alt R.